Right. So we have kind of wrapped up our discussion on simple elementary stages, and as I kept mentioning, so these are some of the the basic fundamentals of analog design. We have looked at all the small building blocks of an analog circuit or an analog IC, and now we are kind of going to start putting things together and make an op-amp. Okay, so that brings us to the next module, which is the operational transconductance amplifier, which is also called as OTA. And just in case some of you are wondering about what is this new long term, if you add a voltage buffer to it, basically a common drain or an output stage, a class AB amplifier or something like that, okay, it becomes an op-amp. An OTA plus a driver stage becomes an op-amp. And the reason why we call it as an OTA and directly not as an op-amp, we'll look at it, slightly in one of the following classes. Okay, so but as a precursor to understanding OTA, we have to look at differential amplifiers. Now I know that many of you are familiar with differential amplifiers. What is the motivation? Why do we need differential amplifiers? Okay, so the reason being that many circuits. So what is a single-ended circuit and what is a single-ended signal and what is a differential signal? Okay. All right. So let's say I have a signal which is some VDC plus some A sine omega t. So when I say it is a single-ended signal, what I'm saying is the other reference point is ground, which is at 0 volt, and I have a signal whose DC voltage is, let's say, some VDC, right? And I have an AC voltage which is riding on top of that, and this amplitude is basically A. Okay. So this is what we mean by a single-ended signal, because the other reference point is basically ground. All right. Now, when we talk about a differential signal, what is a differential signal? I'm pretty sure all of you are familiar with this. We have a common voltage, which is called as the common mode signal or the common mode voltage, or DC common mode voltage. Okay. And one signal, let's say the plus side signal is something like this, okay, with, let's say, this amplitude being some B, okay, and the minus side signal is going to be like this, right? Okay, so let's say a VP is the black one, which can be written as VCM plus some B sine, let's say, omega t, and this other signal VM can be written as the same VCM minus B sine omega t. In other words, VP and VM are 180 degrees out of phase, right, and equal in amplitude, correct? So the amplitude is the same, which is B, right? But the amplitude is the same, but they are 180 degrees out of phase, and this is the definition of a differential signal. And why are we so interested in differential signals, right? One major aspect is, if you look at any practical system, okay, I'll give you a scenario. Let's say this is your chip. Okay, let's say this is some, let's call this as this is some clock generation block, and the clock and clock bar are running, let's say, all around the place. Okay, these are clock lines. This is clock, this is clock bar. Okay, now what is happening is, let's say you have some analog, this is routing. Basically, this is a chip. Let's say you have some analog part here. Now many times, and you have another analog block here, and you have some analog routing here. This is just an example. Now, if you have, let's say, a very tiny analog signal, which is going to be like this, okay, or let me just take the example of a sine wave because it just makes things easier. So if it were a single-ended signal, now because of this clock transition happening, okay, if you zoom in this area, okay, let's say this is your clock signal, and let's say this is your analog signal, right? These are two metal lines. Now what will happen is you will have some capacitive coupling between the two, okay? Because physically, let's assume that they are proximal to, some clock line. You typically try to avoid this as much as possible. I'm just giving you a scenario, okay? Now what happens is this clock is an aggressor, okay? So now this clock line will have some distributed resistance, right? This will also have some distributed resistance, right? Now what happens is this becomes a kind of a high pass filter from this point to here. So it's like a capacitive coupling capacitor to the resistance of the analog line, okay, going to your source, or in the other side, let's say it's going to some ground, okay, or even whatever it is, some input impedance, okay. Through this, it is going to the R input of your next stage, right? Now what happens is this is a high pass filter, right? It's an RC filter, which is a high pass filter. Now, because of this high pass filter, let's say you have a clock waveform like this, okay. What happens? A high pass filter is a differentiator in the time domain. You'll basically get some glitches like this. Okay, sorry. Oops. So this waveform, sinusoidal waveform, instead of just being a sinusoid, you will probably get a glitch like this, a glitch like this, a glitch like this, a glitch like this, and so on. Okay. Now, this glitches, of course, the magnitude of it will depend on the amplitude of the clock signal, how close they are, how well it is coupled, and what is the input impedance, and so on. So if your input impedance is less, probably the effect is lesser. If you're far away, the capacitance is lesser, so the effect is lesser. So all these factors come into the picture. Okay, and if your analog signal happens to be a very tiny, feeble signal, let's say it's coming from some sensor. Okay, now don't think this is a fabricated thing. This happens often. Okay, and especially when you talk about SNR and those things. If you look at the spectrum of this signal, okay, this signal spectrum, if you draw as of now frequency, okay, let's say your signal spectrum was something like this, you will have one spike here, okay, if you draw the spectrum, okay, and this spike is because of your clock, okay, and this is actually a nightmare for many analog engineers. And when you talk about SNR, what happens is this is also called as the spurious free dynamic range, okay, especially in the context of ADCs and so on. So this clock signal, even though this amplitude is small, it will go and sit somewhere there, and it will ruin your SNR, it will ruin your SFDR and things like this. Okay, so this is a problem. Okay. Now, one way to get rid of these things is basically to use differential signals. Now, by differential signals, what we are saying is, now we just assume that there is some clock line running here, and you have, let's say, this is your VP, and let's say this is your VM. I'm just deliberately making them symmetrical, okay, to illustrate the point. So what happens is, let's say this is your VP. You have your sinusoid here, and let's say this is your VM. Oops. Yeah, VM. It's the same VCM here, VCM here, and you have your just assume that it is symmetric. Anyway, now what happens is this clock aggression. Let's say it's happening here. It happens in the same way. Okay. So the aggression becomes a common mode signal. Okay. Now what happens is when you do Vp minus Vm, okay, the aggression or the coupling from clock line is symmetric, or in other words, it's common to Vp and Vm, and therefore gets cancelled. Okay. So in fact, this is the one which kind of saves the day for many the circuits which are basically in use, including the circuits which are inside your laptops and your cell phones and so on. Okay. Differential signal, you have in a more generic term, you can call what is called as a common mode disturbance, or more professionally it's called as common mode noise. Okay. Common mode noise basically is the noise which is common to both Vp and Vm, the two differential signals. Okay. And the point with differential signals is, if we use a differential amplifier or a differential system, the common mode noise can be Cm noise gets eliminated. Okay. Now this common mode disturbance, common mode noise can be anything. Okay. It can be a power supply line which is coupling to your signal line. It can be anything else. Okay. But what happens is, this differential line, as long as it is symmetrically coupling, if you use a differential amplifier, you can get off it. Okay. So now our task now is to see how we can design a differential amplifier. Okay. So what is a differential amplifier? So in other words, if you have, let's say, let's just get some basics done here. So if signals V1 and V2 are there, present, okay, and they are nominally, let's say, differential. Okay. So the differential mode signal is basically VDM is nothing but V1 minus V2, or the difference between the two. The common mode signal can be taken as V1 plus V2 divided by 2. Okay. So this is an important definition. Just keep it in mind. Okay. So even I mean, this works for both DC as well as any kind of AC disturbances. The differential mode signal is given by V1 minus V2, and the common mode signal is given by the average of the two signals. Okay. All right. So now let's design a basic differential pair. What is a differential pair? Now you would say, okay, let's say we are using a common source. Let's use the basic common source. We take two common source amplifiers. Okay, let's say this is given to Vp and this is given to Vm. Okay, let's say both the transistors are identical. Okay, so M1 and M2 are identical, and as indicated, resistors are the same. All right. Now you will have, let's say this is Vout1, this is Vout2. Now if you take Vout1 minus Vout2, you can say that this becomes a differential pair in some sort of term. But this circuit has a problem. Okay. Now if everything, we are right now assuming that M1 and M2 are perfectly matched and this resistors are perfectly matched. Now by now all of you will be familiar that that is really not the case, but we will see its effect probably in the next class or so. But right now we know that if you take Vp and Vm as input differential signals, Vout1 and Vout2 will become the output differential signal. But there is a very fundamental problem. Okay. Now what is the problem? What if the common mode VCM in, okay, I am denoting it as VCM in, which is the common mode voltage, okay, or rather the DC common mode voltage, is not steady. What do I mean by not steady? For example, for some point of time, let's say the input signal V in CM is, let's say, 0.7 volt, assuming it's a 65 nanometer technology. Okay, and then suddenly it changes to, let's say, 0.65 volt. Now what will happen? Your V in CM, V in common mode is basically your VGS1 and it's equal to VGS2. I'm writing capital VGS to denote that it is the DC bias. Okay. Now when VGS changes, what will happen? Your ID will change. Okay. Now when VDS and ID change, your GM R not change. Correct? Now if these things change, what happens? Obviously your gain, bandwidth, noise, signal swing, limits, etc., they all change. Correct? So in other words, what is happening is your input common mode has changed, okay, due to some reason. Okay, sometimes you cannot even predict it. Let's say you have a previous stage which will nominally be around, let's say, 0.7. It can be can go to 0.7 to 0.75. Under some circumstances it can go to 0.6, 0.65. Now what happens is your gain keeps changing. Suppose your common mode voltage just drops down, okay, and then it reaches very low voltage. What can happen is, let's say if this is your volt, okay, and let's say your common mode voltage suddenly dropped from a higher voltage to a common mode prime, where let's say this is your VTH, okay. Now what can happen? Your differential signals can go below VTH. That means what will happen to your output? Okay, let's say I am drawing the other signal like this. Okay. Now what will happen to your output? This is T. Let's say V out. Now V out will become, the red one will become, like when it is low, it will go high, and then so on, and then it will start clipping. Right? When the voltage becomes very low, so V out is basically V out 2, then I mean if the voltage, I mean V out 1, so what will happen if the voltage goes very low, this will start going to VDD. You'll have clipping. Okay, so your input common mode voltage is doing a lot of unnecessary things. Okay, so is there a way to stabilize this circuit for different ranges of input common mode? Okay. Even if you assume that it's not going to this clipping range, okay, can we stabilize this circuit? So the solution to this is basically given by having the same differential pair, but what you have is you're tying both these differential pairs to a common current source. Okay, so basically you are putting a current source. Let's call it as the tail current source. Some people call it as ISS. Okay, whatever you call it, that is up to you. Okay, now what happens? Let's say this is VP, VM. Let's still call it as V out 1 and this is V out 2. So all I have done is taken the same two common source amplifiers and tied them together to a common tail current source. Okay. Now let us see what happens if V in common mode changes. Okay. If V in CM changes, what will happen? Let's say it is, let's take the example that it is increasing. Okay. Now if it is increasing, this tail current source at the bottom is going to fix the total amount of current. Okay. So at DC, okay, that is to say that VAC is 0. Okay. VP is equal to VM is equal to V in common mode. That is, there is no small signal riding on top of it. It's only DC. VP and VM are both equal to V in common mode. What will happen to, let's say this is I1, this is I2. What can you say about I1 and I2? Guys, you can unmute and answer, please. What can you say about
ISS by 2. Could be
Exactly.
half of ISS.
Yeah, I1 and I2 together will be equal to ISS, and because both sides are identical, I1 is equal to I2 is equal to ISS by 2. It's not very difficult to prove because you have, this is a common point. Let's call this node as point P. Okay, you can say that V in common mode is the same, and therefore Vp is a constant, and so both transistors have a certain VGS. Both transistors are identical. So if both transistors are identical, that is their dimensions are the same, VGS is the same, obviously the current will also be the same. Okay, and obviously VDS will also be the same. So both currents are equal, and if you do KCL at this node P, I1 plus I2 have to be equal to ISS or ITAIL. And because both are equal, you can say that both arms of the differential pair will have the same current. So this is a fundamental property of differential circuits. Now if VCM increases, okay, now what will happen? Both VP and VM are increasing, right? But then ITAIL is fixed. Okay, so what will this transistor do? Your gate voltage has gone up, your W by L is the same, and your current is also the same. So which means that your VGS1 will be equal to VGS2, equal to a constant. Okay, because the current is being fixed by this current source at the bottom. All right, so you cannot go beyond ISS, right? So then what will happen? It will take only VGS that is required for the transistor. Let's call it as VGS naught. Okay, and this voltage across the tail current source will be V in common mode minus VGS naught. Okay, so whether the input common mode increases or decreases, the gate to source voltage of both the transistors will remain the same because the current is fixed. You're basically, it is like, you know, putting you in a running track and tying your legs to a chain, okay, and tying it to a pole. Okay, so even though you have a nice running track in front of you, even though you want to run, because your legs are tied, you cannot run. Okay, so it is like that. Your tail is, I mean, the tail current is fixed, the current is fixed. So although you have an increased or a decreased voltage at the gate, the VGS remains the same, and the rest of the voltage drops across the tail current. This is a very important property that you should know. Okay, now again you can come back and say that there are obviously limits here. Okay, can we talk about the limits? What is the min? What is V in CM min? What will be the minimum voltage for this one? Okay, before we see that, what right now we have already come across current sources and current mirrors. So what you can do is you can, you know, replace this current source with a transistor, which is, let's say, you know, you have some current source, you have a current mirror, okay, and it is biased. Okay, right now we are not so interested in the biasing arrangement. Okay, so basically let's just say it is given some bias voltage VB. Okay, so let's call this as M1, this is M2, this is R. Okay, both are R. Let's call this as M3. Okay, now what is the V in common mode minimum? In other words, can we keep decreasing the input common mode, or will something else happen? What happens if you just keep dropping the input common mode signal? Well, I'm
Cannot
waiting for your
maintain
answer.
current.
Sorry? Can you repeat?
It cannot maintain that current flow.
Exactly. You can't maintain the current flow. Why? Why is that so?
M1, M2 will go out of saturation.
M1, M2, yeah, that we will look at it probably when we look at the maximum. Before that, what happens? Okay. One way to understand this is like let's say we are looking at, these two connected together to V in CM. Okay, this is the way we are analyzing it now. Suppose V in CM is dropping, what will happen?
Transistor go to cutoff.
Yes, two things can happen. One is M1, M2 can go into cutoff. That is that's the second step. But before that, what will happen? Even before M1 and M2 go into cutoff, let's say you have
M3 will go to triode region.
Exactly. M3 will move to triode. Okay, because this M3 needs VDS sat across the drain to source, across this drain, right, in order to have M3 in saturation. Okay, so if you assume the square law model, V in should be at least equal to, let's say, VB minus VTH, correct? But V in CM should be this plus the gate to source voltage 1, 2, correct? So your V in common mode has to support the VGS for this current plus the triode, the minimum voltage required across your current mirror for it to work as a current source. Okay, so is this clear? So your minimum, so if suppose for this transistor M1, you do a design and then you find out for a certain W by L ratio, right, you have to have 0.4 volt as VGS, and then let's say VB is also given as 0.5 and let's say VTH is 0.3. So basically you need 0.2, which means your minimum input common mode should be 0.6. Okay, so now when you design your differential amplifier, okay, what you need to do is first look at what is the input common mode. Okay, where is the input common mode coming from? Okay, suppose for example, I mean, this is how you design it. This is the design problem. Let's say it is known, given to you, that the previous block's common mode voltage is, let's say, 0.5 volt. Okay, I'm talking about a 1.2 volt system, let's say a 65 nanometer technology. Okay, your input common mode is at 0.5 volt. Okay, now you're stuck with that. So which means what? You have to make sure that VDS sat plus VGS is less than 0.5 volt. Okay, so you can budget it. You can say, okay, I'm going to budget 0.3 here, and I'm going to budget some 0.15 here, and that way I'll be able to have some margin as well. Okay, so now what happens? You are having 0.3 as your VGS. You go to your curves, okay, and then you look at your ID VGS, right? You say, okay, at 0.3 volt for some W by L naught, what is the ID naught that I'm getting? And I want, let's say, 500 microamps to flow through this, and therefore I will go and scale my W by L ratio such that I'm able to meet my current. Okay, so if so you will basically do 500 microamp divided by ID naught into W by L naught, and this will be your W by L for 1. You understood? Okay, so this is the way you design. Okay, but typically when you have very low voltages like this, okay, 0.5, where you are kind of getting crunched down, the simple solution is to go for a PMOS. Okay, how can you do a PMOS? You basically just put the whole thing ulta. Put a current source at the top, and then you have a PMOS input pair. Okay, so this is VP, this is VM, and then you have resistors to ground. Okay, so this becomes Vout1, this becomes Vout2. Now what happens? You basically need a certain VSG plus some VDS, VSD SAT. Okay. So if your V in common mode is low, the solution is to go for a PMOS input pair. Okay. If V in common mode you know is going to be high, the solution is to go for a NMOS input pair. Okay. Because if it's somewhere around half VDD, you can use either of the two. I mean, depending on how you work with it. Okay. There are other reasons also. Sometimes people deliberately prefer a PMOS input pair because it has a little lesser flicker noise. Okay. And because device dimensions typically are a little higher, you get better mismatch and things like that. But otherwise, people prefer people use NMOS. Okay. So in fact, if you look at if you go through the circuit of I think your op-amp 741, I think it has a PNP transistor. Of course, that's a BJT op-amp. The input pair is a PNP transistor. Okay. All right. So now coming to the to this one, so we looked at what is the minimum input common mode that you need, and depending on what is required. So sometimes you can go and tell, okay, I want you're designing the block before mine. I want an input common mode at this particular voltage. You give it to me. Okay. So then that works like this. Sometimes it can also be that your manager comes and tells you your input common mode is going to be from 0.5 and above. Okay. So design accordingly. So then you have to design based on that. Okay. Now let us look at what is V in common mode max. Can you keep increasing it arbitrarily? Okay, that is the question. So let me draw the circuit once again. Think about it and tell me. Look at the circuit. Can we increase it arbitrarily? Let's say I'm taking it to some very high value, 1 volt or something like that. VDD is 1.2 volt. Let's say I am tying both my things to V in common mode. What will happen? Let me give you a clue. M1 and M2 should be in saturation. Okay, anyone? I hope you guys are following.
It will go into the triode region.
Yeah, why will it go into the triode region? You're right, but why will it go into the triode region?
Because the VGS will become less than VDS plus VT. So
correct. So basically, this is, let's say, V out DC. Okay. Now V out common mode, okay, can be written as what? VDD minus ID times ISS by 2 times R here. Okay. Right. So let's assume that the transistors are the bottom transistor is obviously in saturation. Okay. But this V out common mode is at a certain voltage. Okay. Or in other words, let me write it as VCM out is at a certain voltage. Okay. Let's say this is at some let's say this is at 0.8 volt. Okay. Now what is happening if your input common mode keeps increasing? Your VDS should be always greater than VGS minus VTH for this transistor M1 and M2. Your drain voltage is fixed, but then if you keep increasing, right, your VDS is reducing, right? Your drain voltage, let's assume that channel length modulation and all is not there. Okay. So then what happens? V out DC is fixed. Okay, VD is fixed, but this VS point, VS is increasing. Okay, and VG is also increasing, and therefore VGS is constant minus VTH. Now as VS increases, basically what will happen? Your VDS starts falling, correct? This node voltage will keep increasing as you keep increasing V in CM. So VDS will start falling. So then what happens? It reaches a point where the input common mode becomes greater than, the VDS is no longer greater than VGS minus VTH. So what will be that particular voltage? We can write that V in CM minus VTH should be less than VDD minus ISS by 2R minus, what is this? V in common mode minus VGS1. Okay. This is basically your VS. This is your VD. Okay. So with this you can find out what is the input common mode voltage that will give you the max voltage. Okay, you understand? So for a differential pair in this particular circuit, there is a range of input common mode voltages. Okay, and that range is what is called as the input common mode range. Okay, which is basically given by V in CM max minus V in CM min. Understood? Okay. So this is a very important parameter for your op amp. All right. What is the range of input common mode voltages? Okay. All right. Now let's go to the next thing. Now we looked at the input. We looked at the input common mode, right? What happens to the differential signal? Okay. So let us. So let me just mention that this is a critical parameter for op amp design. All right. So let us move to the next topic of large signal differential behavior. Okay. What we did before was a large signal common mode behavior, right? Now we are doing large signal differential behavior. Okay. In other words, what we are saying is your VP and VM are large. Okay. So let's say this is VP and let's say this is VM. Okay. Now what will happen to this circuit if your differential signal is large? Let's assume, now we can assume that the common mode signal is fine. Okay. The common mode signal is well biased. Okay. This is VP, this is VM. Okay. So red is VP, black is VM. All right. Okay. Before I just go into it, let me just go back to this one. Okay. All this analysis, we said that this VGS and this VP, this node VP, this will basically scale, right? This node VP will scale. So as we can just put it as V in common mode, and if you plot VP, you can say that it is kind of 0, and after the point it just basically tracks V in common mode. That's what we understood now. Now all this is fine for large channel length devices. For short channel length devices, as you would very well know, the output impedance of this transistor, right? This is only R03, okay, and therefore due to channel length modulation effect, there will be a little increase in your tail current. Okay, so I1 plus I2, the tail current itself will increase a little bit. That is understood, but to a first order it remains constant. Okay, so when you are doing simulations, don't get shocked that things are going all over the place, because that is expected when your output impedance of your current source is bad. Okay, so that is the thing that we should understand and keep it in mind for for advanced technology nodes. As your input common mode increases, there will be some increase in your tail current source, and there will be therefore a increase in your I1 and I2. So just keep that in mind. Okay, all right. So now let's look at the large signal behavior. Now what do you think will happen if your input differential signal starts becoming large? Can you tell me?
Where it will be clipped in the output.
Correct. It will get clipped. So what can happen? So one thing is the voltage at this point, okay, let me use a different color. This lower point, so basically, if the VP or VM can result in M1 or M2 turning off at the lowest input swing. Correct? So if this voltage goes to, let's say, some 0.3 or 0.2, something like that, now what will happen? This, if you, anyway, the other side, it will be much larger. Okay. So if you look at this is VP, let's call this as some node X then. Okay. So Vx, if you look at Vx, okay, Vx, how will it behave? Basically, this is going up and down like this, and this part is going down and then up like this. Okay, this Vx is the midpoint between the two. If you write a KVL equation from Vp, Vx, and Vm, you will see that Vx is nothing but Vp plus Vm by 2. It's the average point, or rather, it's the midpoint of Vp and Vm. Okay, so this node Vx remains unchanged when you have signal swing. Okay, and so what happens is the current is the same. Now what can happen is, if when at this particular point we are looking at this particular point where Vp is maximum and Vm is minimum, now what can happen is entire I tail can come through one side. Okay, and this side is cut off. Okay, and in the next cycle what happens? The left hand side is cut off and the right hand side conducts the entire I tail current. Okay, so of course when it comes to large signal, Vx will also change, but for small signals Vx will remain fairly constant. Okay, so this is with a star, that is like for smaller signal swings. Okay, so otherwise what happens is, if one side gets cut off, entire I tail has to go through one side, so the VGS will increase to allow for that increased amount of current. Okay, and therefore Vx will go down a little bit. Okay, so that is something that you have to keep in mind. I hope you understood that. Okay, so what can happen is, as someone clearly pointed out, the voltages will start getting clipped, and the voltages will start getting clipped because one side is fully turned off, and so this will reach VDD. Okay, it is totally off, no current flow here, so it will go to VDD. So if you plot, let's say, V in P minus, or rather let's call it as Vp minus Vm, Vp minus Vm, let's say this is 0. Okay, so when it is 0, both the transistors are conducting equal amounts of current, right? So you can say that this point, it can be written as VDD minus ISS by 2 into R. Okay, now as Vp becomes larger than Vm, what will happen? The voltage will start increasing linearly. Okay, for small signals, okay, you will have more linear kind of amplification here, right? And then what happens, as it increases, then it starts saturating and goes like this. Okay, and in the other side, what will happen? As Vp, oh, I'm sorry, it's the other way around. Okay, so as Vp increases, right, the current flow in that path will increase, and therefore the voltage will start decreasing. Okay, so intuitively you can understand it like this, right? So you have these two arms, okay, tied to a current source, assuming that I tail is the same. Okay, so if Vp is greater than Vm, more current will flow through this branch and lesser current will flow through the other branch. Okay, so since more current is flowing here, V out 1 will what will happen to Vout1? Vout1 will basically drop, because Vout1 is nothing but VDD minus I1 times R. So I1 is increasing and Vout1 starts decreasing. Okay. On the other hand, when Vp increases, okay, decreases than Vm, Vout1 will start increasing. Okay. And what happens is, beyond a point, it will kind of come to some kind of a saturation voltage. Here it will reach VDD. Okay. Same way, if you plot for Vout2, here again it will be linear, and then as Vp increases more and more, entire I tail will flow through the left hand side arm, and then you will have VDD here. Here it will come to some lower voltage. Okay. Now this is the behavior of Vout2, and this is the behavior of Vout1. So this is how the differential pair behaves with the input differential signal. Okay. So I will stop with this and we'll continue from next class. All right. So any doubts, any questions? Okay. So thanks everyone and have a nice day. And one more thing. So regarding the project, from tomorrow evening onwards, I'll just give the schedule. So we'll have the 0th review as I mentioned. Okay. So 0th review, all you need to do is just to figure out which project you are going to work on. Okay. Identify the project and maybe just go through some basic stuff if possible. But since I have not taken much of op-amp stuff, we'll just identify the project, and in tomorrow's meeting I'll try to divide the work among yourself, which you can kind of modify later. Okay. So we have Wednesday, Thursday and Friday we'll have the 0th review. So first 3 groups tomorrow evening at maybe 4:15 we will start. Just some 10 minutes per group. Okay. I know that MTech students are having their quiz 2 exam. Okay. But you can obviously spend some 15 minutes or so. We'll just identify your project and we'll see how you can get started. Okay. All right. Okay. Thanks everyone. Have a nice day.